Tour guides call them lightning rods, but the rooftops of Victorian Europe are crowded with far stranger arrays. Webs of gleaming copper, grids running down steeples, cables vanishing deep into cellars. Official accounts never explain why engineers abandoned Franklin's simple design for these complex rooftop systems. Yet hundreds of buildings share this odd feature, built in an age when new science hinted that the sky itself carried usable electric power. So what were these forgotten installations really for, and what evidence proves rooftop electricity was harvested, not just imagined? The answer challenges everything you think you know about the hidden currents above our heads. Across the rooftops of Victorian Europe, metal rods jut skyward in patterns that defy simple explanation. In Leipzig, the spires of St. Nicholas Church bristle with pointed conductors, while Vienna's City Hall brims with copper grids and cables that snake down from domes to the earth below. These features are not rare quirks. They appear on churches, observatories, and town halls from the 1840s through the early 20th century. Yet, when asked, guides and plaques offer only a familiar answer: lightning protection. But Franklin's original design called for a single, sharp rod to channel a lightning strike safely to ground. The Victorian approach went further, multiplying rods, lacing them together with thick copper bands, and often running the cables all the way into the depths of the building. Some installations even included horizontal arms and branching extensions that seemed to serve no obvious purpose if the goal was simply to divert lightning. Architectural surveys and period photographs reveal a striking consistency. These elaborate arrays are not random, nor are they the result of later modifications. Construction records from the era reference the installation of extensive metalwork, but the language is often vague, mentioning systems of conductors or metallic protection networks rather than the specifics of their function. The sheer scale and complexity of these rooftop systems suggest an engineering intent that went beyond the minimum required by law or insurance. The visible evidence raises a basic question: why did so many Victorian engineers invest in such elaborate rooftop networks, and what purpose did all those extra rods and cables truly serve? High above the ground, the air holds a natural electric charge. This invisible field stretches from the surface of the Earth all the way to the edge of space, forming what physicists call an Earth ionosphere capacitor. Under clear skies, the voltage increases by about 100 to 150 volts for every meter of height. By the time you reach the top of a 10-meter rooftop, the difference can exceed 1,000 volts. These numbers are not theory. They were measured and published by Lord Kelvin in the 1860s, using delicate electrometers and insulated wires strung from observatory towers. But voltage alone is not enough to power anything useful. The real challenge is that air, despite its charge, is a stubborn insulator. The conductivity at ground level is only about 1/10 trillionth of a Siemens per meter, a value so low that only the most sensitive instruments can detect the resulting current. Even with a large metal collector perched high above a city, the typical output is measured in microamperes, millionths of an ampere. That is enough to move a needle on a scientific instrument, but not enough to light a lamp or run a motor for more than a fleeting moment. Victorian engineers understood these limits well. Their experiments confirmed that the atmosphere could provide a steady trickle of charge, but only in tiny amounts. Any attempt to gather usable energy from the sky had to reckon with the stubborn reality of physics. Still, the idea was technically sound. The sky held power, if only you could find a way to collect it. This principle would soon inspire inventors to file patents and design experimental apparatus, hoping to turn the faint currents of the upper air into practical energy, however modest. Patent archives from the 19th century reveal that the idea of tapping atmospheric electricity was not just the stuff of idle speculation. Inventors took the concept seriously enough to commit their designs to official records, hoping to turn the faint trickle of charge in the air into something practical. In 1871, Nathan Stubblefield filed a U.S. patent describing an apparatus intended to draw electricity from the earth and air using metal plates, coils, and carefully arranged conductors. His design aimed to capture the natural voltage difference between ground and sky, though the expected output was modest, suitable only for charging batteries or powering low-demand devices. Across the Atlantic, C.F. Varley, a prominent figure in submarine telegraphy, received a British patent in 1860 for an atmospheric electricity collector. Varley's approach involved raising wires high above the ground, sometimes with the help of balloons and channeling the captured current through capacitors. The language of the patent is cautious, stressing the limitations imposed by weather and the tiny scale of the available power. French patent records from 1868 describe a similar system, a network of roof conductors connected to Leyden jar capacitors, with the explicit claim that it could supply enough current for emergency lighting on clear nights. These patents share a common thread. They treat atmospheric electricity as a real, if limited, resource. The inventors did not promise miracles. Instead, they described supplementary systems, always acknowledging the challenges of air's high resistance and the unpredictable nature of the currents. The presence of these blueprints in official archives demonstrates that Victorian engineers approached the problem with professional rigor, not wishful thinking. City engineers and building managers across Europe and America began to treat rooftop metalwork as more than just a safety measure. In Leipzig, municipal ledgers from the mid-1840s list payments for multiple copper rods and heavy-gauge cables installed on public buildings, with entries noting consultations from scientific societies. The records do not mention lightning protection alone, but rather reference system upgrades and conductor maintenance as recurring expenses. Vienna's City Hall, completed in 1883, included a network of copper conductors mapped in the original architectural plans. These plans detail how rods on the domes connect through thick cables that run deep into the building's foundations. The purpose, according to annotations, was to ensure the uninterrupted operation of essential services, though the technical language stops short of describing exactly how. Maintenance logs from the 1890s mention routine checks on the insulation of these collectors and the replacement of storage elements, a term that hints at more than simple grounding. Commercial properties took a similar approach. The Brevoort Hotel in New York, for example, maintained a rooftop tower with a radial pattern of metal arms, documented in period trade journals as part of an auxiliary electrical system. Staff at the Blue Hill Observatory near Boston kept daily records of collector performance, noting on occasion that the trickle of current was enough to keep instrument batteries topped up, especially during clear weather. These systems were never intended to replace steam-powered dynamos or the grid, but for decades they offered a modest and reliable backup, quietly operating above the city streets, their wires and rods woven into the routine of municipal and scientific life. The arrival of municipal power grids changed the equation for every city that once relied on rooftop metalwork for even the smallest trickle of electricity. By 1905, Vienna City Hall had access to a central electrical supply at a fraction of the cost of maintaining elaborate rooftop arrays. In Leipzig, records from 1911 show that installing a modern dynamo cost nearly 8 times more than a basic rod system, but the output and reliability were in a different league. As city grids expanded, the economic logic for atmospheric collection vanished. Buildings that once invested in copper rods and basement wiring quietly shifted to the grid, leaving the old systems to fade into the background. No controversy, no suppression, just a better, cheaper solution taking over. Stories of unlimited rooftop power and secret Victorian energy breakthroughs often surface online, but the evidence tells a different story. Nikola Tesla himself, in an 1891 letter, admitted, "The energy obtainable from the air is minute, barely enough to move the most sensitive instrument." Claims about Thomas Henry Moray's radiant energy device run into a wall. No patent was ever granted, no working model survives, and every demonstration relied on hidden connections or batteries. Anyone curious can check the facts firsthand. Search Google patents for atmospheric electricity from 1860 to 1920. 42 patents appear, each describing small-scale experimental setups, never city-scale power. Lord Kelvin's original measurements and Augustus Waller's reports are digitized and free to read. The science is real, but the output is modest. The evidence is open to anyone willing to look, and the real history is stranger and more interesting than the myths. Today, the ornate rods atop Victorian rooftops remind us how easily myth fills the gaps in our understanding. As technology evolves, so do the stories we tell about it. The real challenge remains, questioning what we think we know and demanding evidence before legend becomes accepted fact.